Um, okay. Yeah, so this week we're going to talk about smart contracts. Um, Smart contracts are a pretty cool innovation that are possible because of blockchains and a pretty important part of the crypto ecosystem. So a lot of things in crypto are built around smart contracts and around the ability to smart contracts, so they're pretty valuable to understand. Yeah, this is another presentation in our Introduction to Blockchain series. I think we're going to have another one by Jason next week, and then we'll just announce the schedule as we go on the Discord. Okay, it's just a pretty simple outline. We're going to start with like an intro to why smart contracts are useful, what they are, and then do like explain a little bit of EVM because it's kind of important to this, understanding how this works, and then just some example smart contracts, and then like a Solidity Ethereum Etherscan demo using some smart contracts. Okay, so starting off with an introduction. So the current kind of model for the way programs run and work is a company will have a private code repository, which they, it's private and they allow like the outside world and users to access via like a website or an app. And we're just kind of interacting with the front end. And so only employees of this company, can see and edit the code that's part of this repository. So, which then that means the company will also get to decide who gets to use or interact with this code, right? Because if they're controlling the front end, the website or the app that users can interact with this code from, then they can decide, okay, we're going to block this IP address, we're going to block this user, or we're going to only allow people from these countries to use the website or the app. And then, that means from the outside world, this is something that's like really it's largely like a black box, right? Because whenever there's a bug, the way it gets fixed is, the employees of the company go to this private hidden repository, or this repository hidden to the outside world, and fix the code and publish it. So when you interact with it from the front end, everything just looks good now. And so, we assume that whenever you want to interact with this product, this website, this app, it's going to do whatever we want it to do, right? Because if that starts failing to work in that way, people aren't going to come use it. But there is somewhat of an assumption still that things are going to work as you would expect them to work, the underlying design. And so this is like a little diagram kind of explaining how it works, where it's like the client, you have the user there, and they interact with the website, and the website then communicates with the servers and the database. And then, kind of somewhere along here, it gets hidden from the user where they don't really see what's going on underneath, right? And you have to kind of assume that what you think is going on behind the scenes. But now, the idea with smart contracts is, what if you completely change this, right? So what if all of this code was publicly available, right? It's published online. And what if the execution of this code is automatic and irreversible, right? Because in the kind of model we were talking about before, you're assuming that when you're interacting with this website or this app, that everything's going on behind the scenes as you'd expect it to. But then the employees of this company that are like developing this code they can do whatever they want to modify how things are actually working under the hood. So if the execution of the code is automatic and irreversible, that doesn't give like this small group of people kind of overwhelming control over it. And then what if, say, this published code is permanent, right? So it couldn't be modified whenever at the whims of the people that, are like running and developing the code for some company. And what if instead of it being controlled, who's able to run these programs, what if it was completely permissionless, that anybody could run this published code? And then this kind of results in a system where you have complete transparency of the rules and how this program works, right? Because if everybody's able to read this code, if it executes automatically, that means everything's completely transparent. Everyone can see how things are going to work and how all these interactions are going to work. And then kind of what this results in is a system like smart contracts. And kind of what I like the description of it as, smart contracts operate on like a world computer. And the reason it's called a world computer is because everyone in the world has access to this code. Everyone in the world has the ability to run it, view it, execute it. And then it's this model is pretty different from the previous model because everyone around the world then keeps track of the state of this entire system instead of just the company that runs or develops this kind of app. And then so like with that given scenario, it's like why would we want a system like that? Why would you want a system to work in that way, right? And one of the like really big benefits is you wouldn't need to trust some third party or some company that's developing the code. You can just trust the published code, right? It's permanent. It's going to execute automatically. So things are going to work as you see them to work. All you need to do is read the code and verify that it's operating in the way that you want it to. There's additionally no need to trust that the code being run by this company is going to act how you want it to. You can take, like, for example, a system of, like, I have my Capital One bank account online, right? And I assume when I, like, press deposit that what's happening, when I press the deposit button, what's going to happen is that the money I'm depositing in my bank account is going to stay under some account allocated to me. But, you know, I'm really just assuming that. I don't actually know that that's what's going to happen. In a system like what we're talking about, you could actually be able to verify and know for sure that what I think is happening is going to happen. And then lastly, a pretty important thing is that there's no need to trust that this company or this third party will change the rules of their system at the whims of what they're thinking. And the issue is, the rules changing and the system changing can be pretty harmful to users. So like a pretty common example is with like social media platforms where they change their rules of what kind of content's allowed, and then users get their accounts banned or blocked for things they're posting when it's like they may have a previous history of doing so. And so the system we're describing, all you have to do, as this image shows, is trust the blockchain. You can see the code on the blockchain versus having to trust some third party. And that's kind of the model of transactions, but smart contracts broaden this to like a wider variety of just running programs and code in general. Okay, then you have to start thinking of how could a system like this be done, or how could a system like this be created, right? And so one thing you'll need is like a universal computer that maintains the state across the entire system, right? Because if you want each person around the world to be able to run this code, you need everyone else who's interacting with the system around the world to see the kind of latest results and the updated state of this entire system or this like world computer at like every other node at every other place around the world. And so if you take something like Bitcoin as an example, which Bitcoin, what Bitcoin does is it maintains a state, like a universal state of transactions, right? So it's a little bit different than what we're talking about with maintaining a universal state of programs being run and execution in that way. But it's kind of similar, and it can be like a good point to start with to think of how you make an entire system with smart contracts. Where an example of Bitcoin, blockchain at UCLA, how much money blockchain at UCLA has in this account must be known to everyone, right? Because when the blockchain at UCLA address wants to pay someone, everyone else must know that blockchain at UCLA has enough money to carry out that payment. And then similarly, if blockchain at USC pays blockchain at UCLA, the new transaction and the updated values must be updated for everyone to see and everyone that's running this Bitcoin software, right? So we need something similar to that, but we need these states that update to not just be transactions of sending some amount of a currency like this. We need to be updating new states of an entire system that's running code and running functions. And so when the code with smart contracts run, what we need to happen is the new state of the network as a result of the smart contract should update for everyone to see. So to make a system that works like that, you need to start putting some different ideas together, or some different like pieces of the system together. And the first part you can look at is accounts. So we're going to need two different types of accounts. The first type, call it externally owned account, which you can just think of that as a user account. So like me, when I'm going to run a smart contract or when I'm interacting with the system, I have an externally owned account that can run these functions or call these functions. The other type of account you're going to need in a system like this is called a contract account. And a contract account is just a smart contract. When you deploy a smart contract to the blockchain, it's going to have an address. That the address will look the same like an externally owned contract, but it's, instead of being controlled by a user, it's going to be the actual code of a smart contract. And then, so to kind of give a visualization of something like this, you can see in this picture below that this externally owned account has two fields that really matter: a nonce, which doesn't really actually matter too much for right now, and a balance field. The balance is just, how much of some currency you have. And then the other example, in the contract account, you're going to have the same nonce and balance, but you're going to have the two things that make it unique and that define the smart contract, which is the code itself and then storage for some variables, right, that the function is going to interact with. And then this really mimics the Ethereum smart contract type of system. And then the next few slides, this is really Ethereum smart contracts. And then, so another thing you're going to need in a system like this is transactions. But transactions in this sense are going to be different than what you normally think of transactions to be. Because normally you think of a transaction as I pay Jason $10. That's a transaction. But we're going to make transactions in this system a little bit more broad, where a transaction is just an atomic operation that changes the state of the network. Which all that really means is an atomic operation is something that will either execute or it doesn't, right? It's something that can't get stuck in some middle in-between state. So if some function or some smart contract's executing and then some error occurs, what's going to happen is that transaction is going to fail and the system is going to revert to the state before the transaction started. So you can either have something succeed, and when you're going from one state to the next, it's going to be the endpoint of the transaction succeeding. Or if something fails, it can't get stuck somewhere in the middle of the program execution or the operation. So there's really two types of transactions you can think of. And the first one is in the Ethereum example, is you're sending one ETH from one account to another, just like a value transfer. And then the other type of transaction that's kind of makes transactions more broad is just running code from the smart contract, or even deploying a smart contract to the blockchain is a transaction. So, if you run a function that modifies some value, some stored data, so from this previous slide, you say you modify some value that's in that storage there, then that's also a transaction, right? So simply, if you look at this picture, all a transaction is changing the state of this entire system, progressing it forward. And then another thing that's part of the system that you'd need is gas, which gas, the word gas is an analogy, but in this system, all gas is that there's going to be people around the world that are running the software and updating the actual state of the network when someone wants to run a function. So in order to do that, users who want to run functions or run these smart contracts, they have to pay fees or actually pay for the gas of doing the actual work to incentivize someone to do the actual work of updating the network, right? And then one of the useful things of gas is it prevents spam, because if it costs money to execute on this network, or to or to have transactions included in the blockchain, or to progress the state forward, then someone can't just come along and have an infinite number of transactions they want to do just to clog up the network. And so gas is an analogy you could think of to say driving a car, because to be able to do things and drive your car, you need to purchase gas, and gas is what you can't just drive around for free. You need to actually have something doing the work of moving your car. And so when operating on the network here, you need to use or pay with gas to make things run. So if you combine all these things together, then you realize you need somewhere to actually operate on, which you can think of that as the Ethereum virtual machine, which again, this example is a little bit specific to Ethereum with smart contracts, but the Ethereum virtual machine, we're going to kind of explain it in the next couple of slides. First, the first idea you need to understand how this works is what a virtual machine is, which again, this is a little bit technical. If you're like a computer science major, you'll have learned of this before, but if not, it's not too complicated. All it really is like you can think of it as like a computer program that exists on its own or can be spun up on any computer anywhere. So it's not specific to some hardware device. It can be run on any, say like any laptop or any computer, and it's emulating like a completely different computing environment. So one of the ways you can think about it is like on my MacBook, I could spin up a virtual machine that's running mimicking Windows, right? So I could have like a Windows software running on my laptop, and that virtual machine has no connection or really relation to my like local files stored on my MacBook. It's like kind of spun up in its own little world. So it's kind of like a complicated way to think of, say, running like a separate operating system on your own like laptop. Kind of think of it like that. And one of the things about virtual machines is that the computing environment spun up by a virtual machine acts the same no matter where it's being run, which is kind of what we need for if you want to run the Ethereum network or Ethereum system locally. So this image gives you a little example of how it works, because on the left is just like your regular laptop, right? So you have your hardware, then you have your operating system, and then you have all these apps that are running on top of the operating system. And then in a computer that's running a virtual machine, you have like the hardware, and then you have all of these separate virtual machines running, and each of those can have their own like OS and have their own apps running on top of that OS. And they're all separately like compartmentalized, you can think of. They're all separate from each other, and they're separate from the host machine itself. So then, if you connect that back to the Ethereum virtual network, each of the users of the Ethereum network, you can think of them as like running the EVM on their own, where when you want to update the state of the system, it's separate from the state of what's going on your own laptop, but it's like this world computer where everybody's running it on their own and maintaining state and interacting with each other through it. So you want to get a single state of this Ethereum network, right? And the way you maintain the state of this Ethereum network is by running this Ethereum virtual machine around the world. And what happens in the Ethereum blockchain is the blockchains where results of the computation from the EVM are stored and where the transactions update the state of it, right? And so these are like a few different visualizations of what's going on. So you have each of your transactions that go in the blocks, and then you have all these separate users with their own state of the network, right? And they're all sharing transactions with each other and updating their networks in between themselves. So the EVM gets a little bit complicated, but I think it's kind of important to understand this is where the smart contracts are actually operating. This is where they're being carried out. Yeah.
Do you have other examples of things that are being that are like used for smart contracts? That,
What do you mean things to use for?
What else can smart contracts do, etc.
Okay, I think I have some more slides relating to that of like what exactly the smart contracts are doing. So if I don't answer that by the end, then I'll try to do it again. But I think the slides in a little bit will answer that. So okay, now we kind of have the definition of smart contracts laid out. Where smart contracts, it's like a program that runs on a blockchain. You think of it as, and then it's deployed by users, and users can interact with them. And also other smart contracts can interact with other smart contracts. But the smart contracts aren't controlled by users, right? Once you have it deployed to the blockchain, you can interact with it, but you can't take it down, or you can't really change it once it's deployed. And then smart contracts also, they have automatic execution that follow the exact rules of the code if you meet the requirements to run the function. So again, this is just another like little visualization of two parties interacting with a smart contract, and then they create transactions. The smart contract creates transactions that get added into the blockchain. And then, so like the requirements of running the smart contract could be something like, you have to pay at least this X amount of gas for it to be run on the network. And you can even add requirements into the code like only some user with a specific address can run this smart contract. But then like once you set that requirement, then it can't be changed. You're stuck with that. And then in Ethereum's blockchain network, the smart contracts are run on the EVM that we were just talking about. Okay, so then to kind of understand a little further about smart contracts, in Ethereum, opcodes are the smallest building blocks of smart contracts. So you can think of opcodes like assembly code, if you guys have taken like a computer science class before, where you write your high-level code in whatever, JavaScript, C++, and when it gets compiled, it turns into a lot of these like much smaller individual like units you can think of that build up the entire program. So if you, this is from an Ethereum website, which these are all of the opcodes, right? So like the smart contracts, which are written in a much higher level language that do like much bigger things, can all be broken down into these much smaller instructions. And there's a lot more of them, as you can see. And so basically, Solidity and Viper are two examples of languages that you can write smart contracts in on Ethereum. And the way, people aren't writing smart contracts in those opcodes. They write it in languages like Solidity and Viper. And then when you compile these programs in Solidity and Viper, they get broken down into smaller units, into a bunch of opcodes, right? And the opcodes are what actually update the state and run on the EVM. And then, so to see an example of smart contracts, there's this is an example of an ERC20 token smart contract. So like right here, this defines the smart contract. I won't go super deep into this because it's everyone's not here to just read code, but this is like the compiler version, and then just defining your variables, and then constructor, and then there's some functions down here. So that's just what it looks like. And yeah, so these are just high-level languages that compile down into opcodes. And so there's here's some examples of some smart contracts. So like this last one we're just looking at, these ERC20s. I'll explain some of it because I think some people might be interested. But an ERC20 is just like a token that you can build on top of Ethereum, right? So you're going to need, these are events, which events are just kind of like logging things that happen. And then you have like the name of the token, the symbol, the total supply of the token, and you have mappings of addresses to like how much of this token those addresses hold, right? And then if you keep on going, you can actually see the functions. So for example, like this transfer from function, what's going on here is you have a address that somebody is sending this token from, you have address that they're sending it to, you have the amount, and then what you can see right here, you can see that this is like actually updating that some user, they're reducing this amount of that token from the balance of what they hold. And then it's emitting those events that we saw before that were above. Another example of smart contracts are ERC 721s, which are like NFTs. So if you also go back here, this is, I think that's it. So you can see, again, this is defining ERC 721 smart contract. And you can see events there, and then like the name, the NFT, the symbol, and then, again, mappings for owners. And then, let's see, you can see some of the other functions like transferring transferring NFT, and then there's like burning and minting functions too for NFTs. This is kind of hard for me to see what I'm, minting there. And so, those are a couple examples. And then also smart contracts will create the ability for for DeFi and like decentralized exchanges and stuff like that. So, the fact that with blockchains, the money is now programmable, and with like smart contracts, you can kind of automate sending and receiving, and it's going to execute exactly how the rules of the program are written. It allows for a lot of cool stuff in what's now known as decentralized finance. So, like for example, something like Uniswap, what happens is you have these like liquidity pools, and if someone interacts with a smart contract by like sending, by calling a function to say like swap their token that they're holding with some other token, it's going to automatically execute based on the rules of the function in the smart contract, which this isn't really possible with traditional finance or like the traditional way we work with money. Another thing that's possible are DAOs, which DAOs are decentralized autonomous organizations, and those are managed through smart contracts also, right? Because if you can have this set of rules that anyone can interact with, anyone can work with, and it's like a large group of people now has the ability to all interact with each other, and they don't need some trusted third party to maintain the set of rules of interaction and like the rules of this group. They can just use the smart contracts to do that. And then obviously it allows for like the voting mechanisms and things like that for DAOs. So one of the other things that happens now because of smart contracts is hacks become very common. I don't think this is exactly up to date. This is like an old screenshot. But since, as we said, one of the like aspects of smart contracts is that the deployed contracts and the code in those contracts are permanent, security becomes really important, right? Because if there's a bug or some loophole where someone's able to call some function or like that where they can pretend to be someone else, and they're able to take some money out of a contract that they shouldn't have been able to take, the code's kind of stuck like that. But there are some things like circuit breakers and upgradable contracts that allow for that to be mitigated, but that gets like a little bit more into the weeds of it. So another thing is like there's a lot of preventative measures you can take to try to stop your smart contracts from being hacked, where there's like a lot of really like security auditing is very popular, and there's a lot of bug bounties where someone can post their smart contracts and they can offer some amount of money for someone to find any bugs in it. And then something that's pretty useful when developing smart contracts are also test nets, where a test net you can think of is like a replica of, say, if you're trying to develop smart contracts for Ethereum, if you're deploying your smart contracts straight to mainnet Ethereum, then it's going to be expensive, and you don't want to run the risk of losing real money. So there's these test nets that you can think of it as like fake money, fake Ethereum, fake like a kind of fake environment, but it mimics, or it's like a replica of the real environment. So, like Sepolia is a test net for Ethereum, and the tokens, the ETH tokens used on Sepolia are given away for free through faucets. And test nets are managed by the Ethereum community, developers, and other organizations in the space. Because if you think about it, it's like, why would I be incentivized to run this and maintain this? It's all like, you're not making any money off of it. There's no real money involved in it. But if you have a company in the space or you're working in the space, then you greatly benefit by more people using Ethereum and more applications being built on Ethereum, right? So if you maintain test nets, or these companies maintain test nets, more people are going to be able to develop better applications and smart contracts, and then that kind of incentivizes more users to use their products. And then so there's this website Etherscan, which some of you guys may know about, where this is Etherscan for the testnet. So people that are like deploying contracts and have transactions going on in the testnet, Etherscan tracks all of it. So you can look at anything here where, latest transactions from this account to that account, the latest blocks, all of that kind of stuff. And so, like right here, this is an example smart contract someone deployed to the Sepolia testnet, and you can see who created this contract, the balance of the ETH in this contract. You can see transactions with this contract, and then you can actually verify and publish the code here. So that's what this is. And then additionally, what gets stored onto the actual blockchain is the bytecode, which is just those opcodes that the Solidity code gets compiled down to. So that's what this is. And then those events that we were talking about before, those get logged here and show up here when people interact with the smart contract. And then, so what I saved for the end was a little demo of just a super simple smart contract and how you can interact with it on a platform like Remix. So, let's see. Okay, this is going to be kind of tough, or I'm just going to move a little bit so I can actually see this. Okay, this is a smart contract, right? The name of it is just send ETH. This is the compiler version. Are you dimming the lights, Alan? Okay. Yeah, it would probably just be a little easier to read. Okay, yeah. So these are just a couple events, ETH received, ETH sent. And then the purpose of this is whenever ETH is sent to the smart contract, what's going to happen is this handle ETH function is going to be called. And then all this handle ETH function requires is that you send some amount of ETH. And then what's going to happen is half of the ETH that's sent is going to be then sent again to this person recipient. And this person recipient right here is this address, which is just, if you look at my MetaMask, is just this, this guy right here, this address. So what should happen is if I deploy this contract and I send 1 ETH to this contract, automatically what's going to happen is half of that ETH is going to be sent to this account right here. So basically, I'm just going to compile this contract, and then we're gonna deploy it to Sepolia testnet. So here we go, and then just gonna confirm the transaction to deploy it, because again, it costs some amount of ETH to deploy this contract. But since we're doing this on the testnet, right, this isn't real money I'm spending. This is just ETH from a faucet. And then so I confirmed it's going to take a second for this contract to be deployed. This was an old contract I deployed right there. And then, okay, so it's done now. Now the contract's on the blockchain, and this contract has an address right here. So if I go to Etherscan, and I paste in this contract address, I can actually see this is the contract just created 16 seconds ago, right? It's created by this address. It has 0 ETH, and then you can see these other things. So what we're going to do now, see if this works correctly, is we're going to take the address of this contract. I'm going to go to my MetaMask, and what I'm going to do is I'm going to send, I'm going to using this account, I'm going to send, oh, I don't have much. Okay, well, I'll just send 0.1 Sepolia ETH from this account. And so right now, if you look, this account where it's going to be rerouted to from the smart contract has 0.52. So if I send 0.1 ETH from this account, this should end up with 0.57 ETH, right? So, okay, I'm just going to send.
Well, I think you deployed it from that application.
Oh, shoot, did I not?
Yeah, because it didn't switch in the confirmation screen, so if you do it from the other way, it should work.
Wait, what are you saying? I deployed the contract from this account?
Yeah.
Yeah, it should be fine.
Oh, okay.
Yeah, so this was the account address. So I'm going to send 0.1 ETH to this account address, right? And then, so there's going to be a fee with sending it. Going to confirm it. Now this is going to take a second for this transaction to be mined, included in the next block. I'll speed it up. And so once this is done, this value should be updated, right? So I sent it 0.1. So this would originally hold 0.1, but then should be updated to just have 0.05, right? So 0.05, and then what this is going to do, if I go to that other account, yeah, it has a 0.57. So it just received that other 0.05. And then like also what I could do with this contract is this was the bytecode, and then I could like verify and publish the source code from here, there, so anyone can see it on Etherscan. And then these are just the events that get logged of when running the functions. Okay. And yeah, so that was all. All right, thanks for coming, guys. And we do have food that Alan got the